Okay, thank you so much for all the support. Uh, okay, let's get started. Thanks for everyone coming to this presentation. I'm Tianshuo Zhou, currently a PhD student in Oregon State University, and it's really an honor to be here to present the work on RNA design. So first, what is RNA design? We know that the RNA sequence the RNA is actually a sequence of nucleotides, ACGU, and it turns out that RNA is very like our human language or natural language in the sense that it will fold into some recursive secondary structure. So RNA design is the inverse problem of RNA folding. Given a secondary structure as input, RNA design is to find a sequence X such that X would fold into Y. However, for usually an RNA sequence can fold into many different structures. The most important one is the structure with minimum free energy, which is called a MFE structure of X. So one popular design criterion is to find an X such that um, the MFE of X is equal to Y. However, there can be multiple structures with the same minimum free energy. So a stricter design criteria is to let the Y to be the only MFE structure of X. From the perspective of optimization, it means that if the structural distance between MFE of X and Y can be minimized to 0, then the MFE criteria would be satisfied. On the other hand, the physical model of free energy also defines a probability distribution of X fold into different structures Y, normalized by this partition function. One problem with the MFE criterion is that the MFE structure, the probability of MFE structure can be very low. For example, we say the structure C is the MFE structure of this RNA sequence, but there can be many other structures with only slightly higher free energy. So in that case, the structure C, the probability of structure C can be arbitrarily low. Another issue is that under the MFE criterion, all the other structures are totally ignored. But intuitively speaking, we would prefer that all the structures are similar to the target structure. So alternative objectives have been proposed. They are called ensemble-based objectives, including probability defect and ensemble defect, or normalized ensemble defect, NED. So in the second section, I would introduce our proposed method. But let's first look at the general approach for RNA design. So usually, RNA design starts with some randomly initialized sequence, and then the sequence would be mutated and evaluated. If the MFE is satisfied, the algorithm would stop and output the MFE solution. Otherwise, it would go over the process of mutation and evaluation repeatedly. So in our work, we propose the new paradigm named structure-aware multi-frontier ensemble optimization, which has several innovations. First of all, we optimize ensemble objective to overcome the drawbacks of MFE criterion. Secondly, we have a series of structure-aware operators such as structured mutation, to really leverage the local structure information. Last but not least, we this multi-frontier search instead of greedy search to make the optimization process more effective. Now let's zoom in to get a closer look at different components. We first invented a simple yet effective initialization rule. We just make the initialize the unpaired position as A and paired position with CG or GC randomly. But why? The first explanation is that the CG pair has lower free energy compared to other kinds of pairs. And the second reason is that in this way, the unpaired position A will not be able to pair with C or G. Moreover, the probability of an unwanted pair happening would be 1/2 because it's either C or G. The probability of undesirable helix with H stacked pairs would be 1/2 to the power of H, which is extremely low. And then we compare the multi-frontier search with the traditional greedy search. So in the greedy search, the new sequence would replace, at each step, the new sequence would replace the old sequence if and only if the objective gets better. But that can lead to local optima or get stuck in local optima. So in the multi-frontier search, at each step, the top K sequences or the best K sequences in the history are kept in the hope that the local optima can be avoided and more MFV solutions can be found. In the sampling stage, we have two specific samplings. So the first sampling, we sample one sequence from the K-best sequence. And in the second sampling, we sample one position from n possible position. For both sampling, we use the Boltzmann distribution, also known as softmax distribution in machine learning, and we give the hyperparameter T to control the sharpness of the distribution. When the temperature T is low, the distribution is close to one hot distribution. And when the temperature T is high, the distribution would be close to uniform distribution. And after the sampling, mutation can be carried out to generate a new sequence. In the traditional mutation, at each time, only a single pair, a single base, or a pair of bases would be mutated. However, neither of them is a unit in the energy model of RNA secondary structure. In the real energy model, the RNA secondary structure would be decomposed into some local structures such as hairpin, helix, multi-loop, interior loop, and so on. Based on this insight, we propose the so-called structured mutation, which in essence is to mutate all the bases within the same local structure simultaneously. So for the paired bases, we would mutate them with the stacking position together. And for the unpaired positions, we will mutate them with their adjacent pairs together. So in total, we have 6 types of structured mutation. And finally, I would like to highlight how we generate an MFE solution, since our objective is not structural distance. Actually, after each evaluation of the new sequence, we just check whether the MFE condition is satisfied. If it's satisfied, we just output it in our results. But it's just a byproduct and wouldn't affect the optimization process. We can see that along the way of optimizing the probability defect, there are many MFE solutions can be found. So in the third section, I will show our main experiments results. We first used the benchmark Eterna 100 to test the RNA design ability of different methods. So this Eterna 100 contains 100 challenge puzzle from this Eterna website. It is a crowdsourcing platform for human players to perform RNA design tasks. We have two versions of our method, sample optimizing ensemble defect and probability defect respectively. And there are 6 baselines. Let's first look at how many puzzles each method can solve out of 100 puzzles. We can see that our method can sample can solve 77 and 74 puzzles by MFE and unique MFE respectively, outperforming most other methods except for NEMO. But it turns out that the slight advantage of NEMO comes from some human crafted rules in its package. If we use the optimization-based NEMO without rules, our method will be the best performing method in terms of MFE. And importantly, we found that if we look at this Venn diagram, with most puzzles that can be solved by other methods can also be solved by our method sample. And here are 2 examples. Is a puzzle that our method cannot solve, and another example is the puzzle that only our method can solve. We then compare for each solved puzzle how many MFE solutions each method can give. So we can see the method sample can generate tens of thousands MFE solutions for each of the solved puzzles, which is much more than the results of other methods, because other methods can only output at most less than 200 MFE solutions. And if we even if we use ensemble metrics as design criteria, we still found that our method is the best performing one with the highest probability, lowest ensemble defect, and lowest positional entropy. Moreover, our method is fast. We can see the method sample is only slower than Moderna, but the metrics in the table is much better than Moderna. So our method, overall, our method achieves the best trade-off between running time and design successfulness. Even though the Eterna 100 dataset is widely used, its length is limited by 400. So we further test the RNA design for long sequences using the MFE structures of 16S RNA folded by the 2 Vienna RNA. And we found that only our method can solve all the long puzzles by MFE and unique MFE. And another striking observation is that the structure probabilities designed by other methods are as low as 0. And only the method Ensemble can design structures with meaningful probabilities, which demonstrates the huge advantage of the method Ensemble. So to summarize, in our work, we propose a simple yet very effective approach which can solve more puzzles for RNA design and generate high quality MFE solutions in terms of ensemble metrics and can output very large quantities of MFE solutions. And for the long sequences design, our method even have greater advantage. So for the future work, there can be multiple extensions. One is that we can try to prove or validate that some of the puzzles in the Eternal 100 are actually unsolvable under realistic, under the real energy model. Another is that it's the first time that there is a method can generate thousands of MF solutions for each puzzle. So we can really utilize utilize these solutions as training data for the learning-based RNA design in the future. That's all my presentation. Thank you again for your attendance. And feel free to ask questions if you have any.
Thank you.
So we do have time for questions. Yeah, I can start with one. Can you hear me well?
You mentioned at the end that you could now have a training data set for a supervised learning approach. How would you design such an algorithm? How would you represent the data and structure the algorithm?
Yeah, that's a very good question. I mean, currently, most of the RNA design methods are optimization based. So, because the task is very hard, so if we have a lot of puzzles and we can use this our method to generate the answers for the puzzles, then we can have a lot of the supervised data, right?
Yes.
And then, I mean, because currently the available supervision, the available MFE solution is much more than before with the open source of our method. So in this way, I believe the results the results of supervised learning can really be improved.
Okay.
Yeah, just benefiting from the large amount of training data.
Okay, thanks. Any other questions? Yes, Marcel. Maybe I'll repeat the question for him. That can work.
So my question is, it shows that they find a lot of MFE solutions.
Yes.
I was wondering which parts are similar in these solutions and which parts are different.
So the question is, you find many MFE solutions. What is common to those solutions and how do they differ?
Pardon?
You find multiple MFE solutions. What is common to them typically and how do they differ?
How do they differ? Yes, actually, we have. Yeah, that's a very good question because that's actually a question, the same question asked by the reviewer of ISMB, and actually we have supplementary materials to compare the diversity of the different MFE solutions. We can see actually not only actually for other methods they can also output multiple solutions, but it's just that their numbers are such smaller compared to others. But anyway, we can compare the diversity by by the for example for each position we have ACGU, right? We can compute the each position the entropy, and then we take the average. Then that's the diversity of this whole set of MF solutions. And we have compared that, and that's really in the supplementary materials with this paper, and is online available. And the result is that the diversity of our MF solutions are quite high. It's probably the best or the second best. Yeah.